And I think that this is working. All right, welcome back to Intro to Speech Understanding. Let me go ahead and move to the directory for our course and then download this week's course materials. All right, so as you see in my directory here, I only have lecture 8, so I'd better fetch the release and then merge the release. All right, and now that I've merged the release, I should be able to change directory in lecture 9 and begin lecture 9. So let's type Jupyter Notebook and get started. All right, as you can see, we have two waveform files this week, as well as a Jupyter Notebook and some homework. All right, so this week we're finally going to start talking about automatic speech recognition. You remember that 2 weeks ago I introduced audio 3 weeks ago. I introduced audio. I told you that we have to be careful not to alias the audio. We have to be careful to sample it at a high enough sampling rate such that every tone that we want to hear is no greater than half the sampling rate. We have at least two samples per period. Last 2 weeks ago, I told you about the Fourier transform. I told you that in every musical chord, there's a set of three tones, and that you can find out what those three tones are by multiplying the acoustic waveform with a set of complex exponentials. That's a set of cosines and sines, and then looking to see at what frequencies the match is the greatest. Last week, I introduced you to the spectrogram and the short time Fourier transform, where you can take a continuously varying signal like speech, and you can do its Fourier transform once every 25 milliseconds or even once every 4 milliseconds in order to see what the frequency content is as a function of time. And that's the information that you need in order to understand speech. And so this week we're going to begin with the same speech waveform that we worked with last time, the a, e, u, a, o. And first of all, we'll detect when there's speech and when there isn't speech. And then we'll use that to break the waveform up into 5 separate segments, one for each vowel, a, e, u, a, and o. And we'll use those 5 waveform segments as models of those vowels. And then we'll try to match those models to the audio in a test data. I'll read in a new file called test.m4a. We can see those files here. We have test.m4a and train.m4a. Train will have those 5 waveforms, a, e, u, a, o, and test will have some other vowels, and we'll have to try to recognize what are those other vowels in that test file. So let's begin with voice activity detection. First, let me read in the file train.m4a, and again, I'll read it in as the waveform speech, fs. So speech is the audio waveform, and fs is the sampling rate, and the audio is the same as before.
A, E, U,
And of course, if you
A,
want to work with your own
O.
voice, please feel free. Go ahead and record your own voice and then read it in the same manner shown here. I just used QuickTime to record my own voice and to give you this waveform, the training waveform. We can plot it using Matplotlib, and just here's the waveform. These 5 vowels, a, e, u, a, and o, and you can pretty clearly see them in the waveform index. And that gives you an indication of how we'll go about segmenting this file into 5 separate segments. We want to get rid of the silence and only pay attention to the place where there's energy. You notice that the signal is either positive or negative, but it's much larger when there's a vowel, and it's much smaller when there's silence. Silence is roughly x of n equals 0, and speech is a much larger amplitude. And you can measure the energy either just taking the absolute value or by squaring the sample and then averaging. So a common tool is the short time energy, which is defined as just the sum over capital N consecutive samples of the squared sample value. That gives you the short time energy over those capital N sample values. So this is basically we chop the speech into frames, and then we calculate the sum of squares of each frames. So I'm going to create speech frames exactly as I did last time. I'm going to chop the speech into frames with a frame length of 25 milliseconds and a frame skip of 10 milliseconds. And then I'll create the energy exactly as shown in the formula. I'll take the sum of the square of the speech frames, and I'm going to sum along axis 1, that is, sum along each row in order to get the energy. I'll then create an energy time axis by taking the the range from 0 to the frame length, 0 to the length of the speech file, with a frame skip of given by the frame skip, and divide by the sampling rate in order to get the number of seconds. And I can plot the result. If I plot the result, we have the energy is in orange. And notice that since the energy is the sum over 25 milliseconds of the squared sample value, the energy is quite a lot larger than the actual signal. If we wanted the energy to be the same as the signal, we might average instead of taking the sum, but let's leave it as the sum. So there's the energy and there's the signal. You notice that actually the energy is quite different for the different vowels. The oo is the loudest, the ah is the quietest, the a and the o are also pretty loud, and the e is somewhat less loud. But all of them are much, much louder than the silence. And so basically what voice activity detection does, VAD, we have to look at the energy and decide whether it's loud enough to be considered speech. We have to choose some threshold. And usually that means we find the loudest energy and then we take some fraction, say 10% of the loudest, or 5%, or 15%. Just choose some threshold, usually with respect to the loudest energy. And we can say that every time the energy is above 10% of its maximum, that's considered speech. And when it's below 10% of its maximum, that's considered silence. And so that's what's done here. This voice activity detection is an array, and this array is a 1 every time the energy is greater than 0.1 times the maximum. Otherwise, it's a 0. And that's done for m in the range of the length of energy. So here, this is a list comprehension where we're taking for m in the range of the length of 0 up to the length of energy. If the energy is greater than the threshold, output a 1, otherwise output is 0. And if we plot that then along with the speech, we can see that that's a 1 basically everywhere that there's speech. Right at the end of the ah, the energy dropped very low, and so at the end of the ah, that's not included with speech. But chopping off that small portion of speech is really not much of a problem. If we wanted to, we could experiment with this threshold. Let's try 0.05 instead of 0.1, and that should give us a little bit more of the ah. We could even maybe go to 0.01, and maybe that gives us a little bit more. So in that way, we get the entire ah and all of the different vowels. All right, so we'll go ahead and use that as the threshold. Now that's our voice activity detection. Now we want to use that to take this input file and chop it up into 5 smaller files, one for each vowel. So we'll find the start times of each of those segments, the end times of each of those segments, and then we'll find the segment. The start time is just m times the frame skip, where m is the frame index from 1 up to the number of frames. And we have a start time if VAD of m minus 1 is a 0 and VAD of m is a 1. So every time it transitions from 0 to 1, I want to mark that as the start time for a segment. And if VAD of m minus 1 is a 1 and VAD of m is a 0, so every time it transitions from 1 to 0, I want to mark that as the end time. And I want to make sure that that's the frame index m multiplied by the frame skip, which is the skip between starts of frames in samples. Once I have the start time and the end time, then I can take that segment of the speech. I can take the speech waveform from its start time to its end time for each of the different segments. And this will result in a set of 5 different segments, each one of which is a NumPy array. Start frames is not defined. Oops, I've got a typo in my notebook. So this is start times, not start frames. There we go. Now it's calculated the segments, and now I can plot them. Segments 0, 1, 2, 3, 4, 5. We can plot them like this. Here's the ah, and you can see that it does in fact look like the ah. Here's the e. You can see that it does look like the e, the oo, the a, and the o, and you can see that each of those look like the corresponding segment excised from the original. And we can listen to them one at a time. Let's listen first of all to segment 0, and then segment 1,
A,
and then segment
E,
2, and then segment
U,
3, and then segment
A,
4. And so in this way,
O.
we've used the energy in order to do voice activity detection. And then we've used the voice activity detection to divide the waveform into 5 separate segments, one for each of the vowels. This is the most sort of the simplest and the most fundamental way to do speech recognition. Already in 1980, it was possible to recognize words by chopping them with silences. When automatic speech recognition first came out in 1980, one had to produce every word with a silence between it. So instead of speaking continuously as I am now, you would speak with a silence between each pair of words. And if you speak in that way, then it's possible to divide the words using voice activity detection as shown here. So in this case, we have these 5 words, a, e, u, a, o, and now we want to use those to create a model that we can use to recognize other speech. An automatic speech recognizer basically listens to speech audio and compares every frame of the speech audio to a set of models. And what we want to do is we want to create 5 models, one for ah, one for e, one for oo, one for a, one for o. And we're going to use those 5 models to compare them to testing data in order to decide what's being said in the testing data. So we'll take those 5 models and we want to be able to compare this ah to some future ah that might sound similar but won't be exactly the same. And so we want to get rid of the pitch because the pitch is not going to matter, and we want to keep only the spectral envelope. And as you remember from last time, we can do that by calculating the spectrogram. Here I've created a frame length of 4 milliseconds and a frame skip of 2 milliseconds. And then I can basically, for each of these segments, I'm going to chop it into frames with a frame length of 4 milliseconds and a frame skip of 2 milliseconds. And then calculate the magnitude short time Fourier transform and then the spectrogram. And I'll keep the spectrograms. I'll create a list of spectrograms, S-grams, and I'll show just the low frequency bins from 0 up to half of the frequency length, and I'll show that as a spectrogram. And I will also set the y-ticks using a frequency axis, where the frequency axis will be the number of bins in the bottom half frequencies multiplied by fs over n in order to convert it from bin index to hertz. Right? Remember that fs over n is samples per second, and n is samples per FFT bin, and so we get FFT bin, hertz per FFT bin. And here's the spectrogram for ah. You can see it has a lot of energy at around 750 hertz and around 1250 hertz. E has energy at 250 and at 2250. U has energy at 2250, 1250, and 2250. Sorry, 250, 1250, and 2250. A has energy at about 500 hertz, and then again at 2500. O has energy primarily at 500 hertz and at 1,000 hertz. So here are my 5 spectrograms. I could, because these are only keeping the information necessary for the vowel, these are already pretty good models of what those vowels sound like. But in order to get something that's easier to do the comparison, maybe I can average across time. Notice that I have almost 300 frames of each of these. I'm skipping by 2 milliseconds between the start of each frame. And with those 2 milliseconds, I have about 150, let's see, I have about 150 milliseconds for each of these. Actually, it looks more like 500 milliseconds for these vowels. And so I don't really need to have this many repetitions of exactly this frame. Instead, I'm going to average along the time axis. I'm going to take this spectrum, but I'm going to take that spectrum and average it along the time axis in order to get a representation of the vowel. So I'm going to take x of m comma colon, where m is the frame index, and this colon here is the frequency index, and create a vector, and then just average that vector over the length of the vowel. So that's what this does. I take the average of the kth spectrogram over just the bottom and over 2 frequencies, and I'll average it along the time axis. And I'll do that for each of the 5 vowels, a, e, u, a, and o, and then I'll plot it. I'll plot that as a function of the label. And I get these models of the spectrum. Here's A, which has peaks at 900 hertz and 1100 hertz, and again at 500. E has a peak at 250 and another at 2200. U has peaks at 250, 1000, and 2000. A has a peak at 500 and then again at 2000 and 2500. O has a peak at 500 and then again at 1000 and 2500. And so you can see these different shapes. Here's the shape of an A. Here's the shape of an E. Here's the shape of an U. Here's the shape of an A. One thing that I didn't show you before, in order to get these spectrograms and these shapes, I did this pre-emphasis trick, where rather than taking the Fourier transform of the waveform, I first subtracted. I subtracted each sample from the sample that followed it. And that trick, as I taught you last time, gets rid of the very low frequency energy and keeps only the higher frequencies. And so by doing that, we can see the difference between what an A looks like, what an E looks like, what an U looks like, what an A looks like. Those 5 vowels now become much more distinct because I've gotten rid of the very low frequencies using pre-emphasis. So those are my models. Now I have a model of each of the 5 vowels. And now what I want to do is I want to use those 5 models in order to recognize some new test data. So let me read in some new test data. So here's the waveform,
E, A, U, A, O.
A, U, A, O. And I want to recognize that speech. Well, first I can just convert it. First, let me just chop it up into segments. So here's the voice activity detection for that. Let me change this to 0.01 times and see if that works. Here I have 0.1 times, but before I was using 0.01. Let's see if that still gives me reasonable segments. Yep, that looks like it's still giving me a nice 7 segments. E, A, U, A, O. And my goal, even though as a human being you can easily understand what was said, my goal is for the computer to similarly easily understand what was being said. So first we'll chop it up into 7 segments. Here's the 7 segments, E, A, U, A, O. You can see differences in the waveform, right? E looks like this, A looks like this, U looks like neither of them, more like E. U and O looks in between, and the A looks something more like A, actually. That's interesting. A looks more like A, and U looks more like E. Maybe because the E and the U both have a very low first formant and a very high, and the A and the A both have a higher first formant. Let's create the spectra. For each of those, we'll create we'll chop it into frames with, again, a 4 millisecond frame length, capital N, and a 2 millisecond skip. Then we'll take the magnitude short time Fourier transform and then calculate the spectrogram, and then we will average it along the time axis in order to create a spectrum. So by doing that, here I have the spectrum of the 0th segment, and you can see that it looks more like an E. It has a very low first formant and a very high second formant. The spectrum of the second segment, you can see that it looks more like an A. Now the peak at 900 and the peak at 1100 are more separated. Up here, they were more together. Here, they're more together, but we have this broad peak at 1000. Here, they're more separated. Here's an E, here's an A, here's an U. You can see the peak at 200 and the peak at 1000. Here's an A, you can see the peak at 500 and the peak at 2000. And here's an O, you can see the very high peak at 500 and a much lower peak at 1000. This O looks really very nicely similar to the O model that we have, right? And so the goal is to try to take each of these 7 spectra and to figure out which of our 5 models best resembles it. We want to say, does this one really match to this one? And notice that although that's easy for a human, it's not so easy for a computer. So look at this. The E here goes from minus 15 decibels down to minus 35 decibels. Whereas in our test utterance, this E goes from minus 15 down to more than minus 40 decibels. And so the range of amplitudes here is very different. What we want is we want to somehow find some measurement that will ignore this huge difference in the range and only pay attention to the shape. We want to say, oh yes, this shape matches this shape. We want to somehow measure the similarity in their shape, ignoring the similarity in their absolute values. And we can do that using something called cosine similarity. Cosine similarity looks at the difference between 2 vectors. We take the spectrum x and we treat it as a vector. We say that each of these measurements is one dimension in this vector, and we plot that as a vector. And we take the spectrum y and we plot it as a vector. And then we measure how similar those vectors are by measuring the angle that separates the 2 of them. Now, you might remember from geometry that the angle between 2 vectors is the arc cosine of the dot product of those 2 vectors divided by the length of x times the length of y. And so we're going to, this is sort of something that you might have learned in trigonometry or in introductory calculus, but this is an angle for sort of the angle between these 2 vectors. This is a formula. We're going to just use the cosine of theta as a measure of the similarity between these 2 vectors. We'll take the dot product of x with y and divide it by the absolute value of x times the absolute value of y. And that gives us a measure of similarity such that the cosine is approximately 1 when those 2 vectors are the same, and the cosine is much, much less than 1 when those 2 vectors are different, right? The maximum possible value of the cosine is 1. Minimum possible value is minus 1. So if cosine of theta is close to 1, then those 2 vectors are almost identical. If cosine of theta is less than about a half, those 2 vectors are very different. And so we can measure these cosines by, for every model, we compare that to every one of the test spectra. We find that test spectrum in that model, and then we take the dot product between the test spectrum and the model, divide that by the square root of the sum of the squares of x of k times the square root of the sum of the squares of m of y. Right? Each of these is just the length of that vector, which is the square root of the sum of the squares. This can also be done using the vector norm, np.linalg.norm. But what that does is exactly this. It takes the square root of the sum of the squares of the samples of x. And so let me go ahead and do that. I'll calculate the similarity between each model y and each test segment k. And you can see here that the highest similarity of the test segment 0, its highest similarity is with E. Test segment 1 is similar to A. Test segment 2 is similar to E. Test segment 3 is similar to A. And then test segment 4 is similar to either U or O. U and O are both quite similar to test segment 4. And so that test segment 4 is kind of ambiguous. It might be an U or it might be an O. Test segment 5 is clearly an A, and test segment 6 is clearly an O. And so recognition then, automatic speech recognition, is simply finding which one of these is maximum and outputting that character. So we'll just take the argmax of cosines of colon comma k in order to find out here the argmax is the E, here the argmax is A, here the argmax is E, A, U, A, O. We want to find that argmax for each one of the columns of the cosines matrix. We'll find its argmax and then look up the corresponding labels. And that will give us the corresponding labels. I will plot the labels as the title. The test output K I'll plot as the title, and the audio test segment I'll plot as the waveform. And so if I plot all of those, we have that the labels are E, A, E, A, U, A, O. So here are the recognized labels, and the automatic speech recognition worked. It generated the correct output label for each of those. That isn't always true. Right, it doesn't always work with 100% accuracy. More more often you'll find that it will make some mistakes, but for this particular waveform, it makes no mistakes. It recognizes all 7 of those syllables with perfect accuracy. All right, so that's automatic speech recognition. You create a model, and you use that model you use the set of models, you compare every single one of those models, right? The key to automatic speech recognition is this double nested loop. For every possible model, we compare it to every possible test segment in order to find the similarity between each of those models and each of those test segments. And that similarity score can be calculated, for example, using the cosine similarity score by taking the dot product between those two vectors divided by the length of each of those vectors, the square root of the sum of their squares. So that's a way that we can do speech recognition. The homework basically does all of those same things. 9.1 does the voice activity detection, 9.2 converts the segments into models, and 9.3 recognizes the speech. So let me go ahead and do each of those homework problems now. First of all, 9.1 does voice activity detection. Given a waveform and a sampling frequency, it calculates the energy in 25 millisecond frames with a 10 millisecond skip. And then it returns a list of arrays. That's a list of segments where the energy is greater than 10% of the maximum. So we're not going to do 0.01 here, we'll just do 0.1, 10%. So let me open homework 9.py. And we don't want a runtime error here. Instead, we want to take this waveform and first of all, chop it up into frames with a 25 millisecond frame length and a 10 millisecond frame step. So we'll say frame length is equal to int of 0.025 times fs, and frame skip is equal to the integer of 0.01 times fs. And then the frames themselves will be a NumPy array, which is waveform from m to m plus the frame length for m in the range between 0 and the length of the waveform minus the frame length with a skip of frame skip. And then close the for loop and close the NumPy array. There are the frames. Now we want to convert that to energy. The energy is just the sum of the square of the frames. And we want to sum along each row. Oh, we don't take the square along each row, we take the sum along each row. Now that we've calculated the energy, now we want to calculate the voice activity detection. The voice activity detection is equal to a 1 if energy of m is greater than 0.1 times the max of the energy, else is 0, or m in the range of 0 up to the length of the energy. There's the voice activity detection. And now we want to find the start time and the end time for each of the frames. The start times are equal to the frames where energy of m, where VAD of m minus 1 is a 0, and VAD of m is a 1. And the end times are the frame indices m, oh, not m, but m times frame skip, right? We want the sample time. The end times are the sample times, where VAD of m minus 1 is a 1 and VAD of m is a 0. And now that we have that, we want the actual segments. The segments are the waveform segments from start times of k to end times of k, for k in the range of the length of the start times. There we go. And then we just return the segments. So what we've done is we've calculated the energy in every 25 millisecond frame with a skip of 10 milliseconds. And then we've said that there is speech present, voice activity detection, when the energy is greater than 10% of the maximum energy. And we've used that to find the start time and the end time of every segment, and then to chop the waveform into segments. Let me go back to the Jupyter notebook and test to see if that gives good results and it doesn't give any bugs. We'll reload the homework and then we'll run the VAD and then we'll plot the results. And well, it looks like I've got a mistake. Start times of k up to end times of k. There's a syntax error. I didn't close that. So let me go back and close that. You need to close that call. There we go. Let's see if that works. Okay, now I still have a problem. List object cannot be interpreted as an integer. Start times. M times frame for M and range VAD. Oh, I'm taking this list VAD and I'm treating it as an integer. I want to take the length of VAD, not just the range of VAD. I want to take the length from 0 up to the length of VAD. Okay, let's see if that was sufficient. Ah, good. There we go. Now we have our 5 vowels: a, e, u, a, and o. All right. Now we've got voice activity detection working. Now let's go on to homework 2. Homework 2 is to convert those training segments into models. I want to take each of those training segments and calculate its spectrogram, pre-emphasize it, then calculate its spectrogram with a 4 millisecond frame length and a 2 millisecond skip, and then keep only the low frequency half of each spectrum and average the low frequency spectra to make the model. And I should return the models, which is a list of arrays that should contain just 5 arrays. So let's try that. First of all, let's get rid of the runtime error here. And let's see, the frame length should be 0.004 times fs, 4 milliseconds. And the frame skip should be 0.002 times fs, 2 milliseconds. And I want to convert that into frames pretty much the same as I did up above. NumPy array of, oh, but I want to do that for every segment separately. So for every segment, I want to chop segments of k from sample time m to sample time m plus capital N for m in the range between 0 and the length of the segment minus capital N with a frame skip of capital S. There we go. That's the frames. And then I want to calculate the magnitude short time Fourier transform. That's the absolute value of the FFT of the frames along the row axis. And then I want to calculate the spectrogram. The spectrogram is 20 times the log 10 of the maximum of 0.001 times the array maximum of the MSTFT or the MSTFT itself. And that way I'm thresholding to make sure that I don't go below negative 60 dB. And now I want to average that. And I want to average just the low frequency half of the spectrogram. So I want to append to the model, I want to append the average over time of 0 to the n over 2. And I want to average that along the time axis, which is axis 0. And then that will give me an array that I want to append to the model. In order to append it, I'd better initialize models as just an empty list. And then once I've done, I can return the models. So now I've created the models, and for each model, I've appended one of these average spectrograms, which is just the low frequency components, the average spectrum, which is the low frequency components of the spectrogram. Let's try running that and see if that gives us the spectra that looks something like this. Oh, and it already works. Oh, but these are too far tilted. Look, I've got so much low frequency here. All of this extra low frequency here means I forgot to do preemphasis. I have to go back here and I have to pre-emphasize this. Rather than just taking the samples themselves, I want to take the difference between neighboring samples. I want to take segments from m plus 1 to m plus n plus 1 and subtract from that segments from m to m plus n. So this difference is called pre-emphasis, and this difference gets rid of all of that excess low frequency energy and keeps only the higher frequency energy. Now it looks much more like an ah, e, oo, a, and o. And so now I have these 5 different models of the 5 different vowels. And now let me actually go ahead and recognize speech. Speech recognition will take in a test speech utterance and given its sampling rate and given a set of models and a set of labels. Each model corresponds to one label, right? I have a model of ah, one of e, one of oo, one of a, one of o, but the computer doesn't know what those models correspond to. I have to tell it by giving it these labels. And basically, I want to go through and compare every model to every test segment. I want to divide the test speech into segments, and then take those test speech segments and compare every segment to a model and output a list of similarities, which is a y by k array, showing the cosine similarity of each model to each test segment, and then also a list of strings, what I think are the best matching strings. So let's do that. First of all, we need to convert the test speech into segments, and we can do that by redoing the 2 steps that I've done so far. I can take the VAD of the waveform, and the waveform in this case is the test speech. And then I can calculate the spectra for each of those. I'm not going to create models, but I am going to create spectra. So let's call that something like spectra, maybe test spectra. So now I have, well, the input is not called waveform, the input is called test speech. Test speech I converted to segments, segments I converted to test spectra, and now I want to basically go through, let me say capital Y is equal to the number of models that I have, and capital K is equal to the number of test spectra that I have. And now I want to create a Sims matrix, which is just zeros to begin with, of a size of Y by K. And then for each Y in the range up to capital Y, for each K in the range up to capital K, I want to find the similarity between test spectrum small y and test spectrum and sorry, model small y and test spectrum small k. And that will be the dot product between, oh, let me create these models the way that I did before. Let me say that the test spectrum is called X. And let me say that the model is called M. And let me take the dot product between X and M and divide it by the square root of the sum of the squares of M times the square root of the sum of the squares of X. Now I've got all of the similarities. Now I want to find the test outputs. For every segment K, I want to append to the test outputs. And what I want to append is the label that corresponds to the argmax of the similarity matrix for that test spectrum. Let's see. There we go. So I'm going to find the label that corresponds to the argmax for that particular test spectrum, and that argmax will specify which one of the models best fits, and then I'll find the label that corresponds to that model. And then what I want to return is sims and test outputs. So I'll return two variables, the similarities and the test outputs. All right, let's see if I've got any bugs. All right, it looks like I've got a bug. What's the bug? NumPy has no attribute 0. It looks like I tried to call, when I wanted to call zeros, I called 0 instead. What I want is a zeros matrix. All right, let's see if that was my only bug. List object cannot be interpreted as an integer. Error retrieving code. So somewhere in my function, I'm interpreting a list object as an integer. That might be in a range, right? That's what I did before. Y is the length of models. K is the length of the test spectra. Range Y should be range from 0 to Y. Range K should be range from 0 to K. Um, well, that's interesting. That's not showing me where the mistake occurred. And so since it's not showing me, let me try just commenting out everything and see if I can gradually add things until it works. All right, let me just comment out everything after this first segments and test spectra, and let's see now if it works, but it won't give the right answer. Cannot unpack. Oh, it's returning nil. Let me let me just define. Let's just take capital Y as the length of the models. Capital K is the length of the test spectra. Let me go ahead and define those and see if that works. And then let me create test outputs as a null array. Let's see if this output would at least generate an output without failing. No, not yet. I've got some kind of really nasty bug here. Bad test speech fs. That looks right. Segments to models of segments, comma fs. All right, that looks right. Let me comment out everything else. And then at this point, I'm just debugging, trying to figure out where the mistake is. And then let me return one comma, let me return one and an empty array. And that will allow me to return, there it will get sims comma test output. It will say, oh, let me just not show the image. And then let's run this and see if that actually returns something. Okay, that returned, good. Let's print sims and print the recognized outputs. Those should both be blank because I'm not doing anything yet. Sims is 1, recognized outputs are blank. Okay, good. Um, let's just start adding lines here and see how much we can add to have it still work. Still working. Let's add the definition of sims and have test it again, still working. All right. Let me add this nested for loop. And let's see if that still works. All right, that still works. Let's add the definition of test outputs and see if that still works. That still works. All right, let's add this output for K and range test spectra. Ah, there's my mistake. Test spectra is a list, and I need to make this the length of test spectra. That was the bug that was causing this problem, I bet. Now I bet I can get rid of these and return the true output. There's the similarities and there's the list. Okay, let me go ahead and plot and show the result. Let me get rid of this print. There we go. Now I've got my similarity matrix and now I've got the returned outputs. E, U, A, O. All right, excellent. So now we've done the homework. Let's check to make sure that the automatic grading code finds that we have no mistakes. And indeed, the automatic grading code finds that we have no mistakes. So at that point, we can go to open up GitHub Desktop and check it back in. All right, we'll commit 2 files and push to the origin. That's taking a while to push those changes, I guess. Actually, that may take a while because this student account on my student account on GitHub does not yet have the waveform files. So it has to push all of those waveform files. Now it's pushed those. Now let's go ahead to my student account on GitHub and see if all of those are showing there. Let me change to my student account. Here we go. Here's my student account. And if I go to Intro to Speech Understanding, indeed, Lecture 9 is now there. And indeed, if I open up Homework 9, we can see that all of the changes have been made in Homework 9. So it should be possible to copy this and then go to the course page. Where's the Canvas page for this course? Now I'm going to have to open up the Canvas page for this course. There we go. We should go to Homework 9. And in Homework 9, it says enter the URL of your copy of Homework 9. If you enter the URL there, then I will grade it as soon as it's done, and you can get 100 points for that assignment. All right, that's all for this week. Let me go ahead and end the recording.